One of the things that we talked about earlier in the year is why the tangent line, where, the curve, the tangent line to curve, where they come from. One of the things was optics. You think back to Galileo Day and those so forth with the astronomy and those kind of things, and the science that was going on at the time. And so the whole idea of optics and reflection and those kind of things, and you get into off of a curved surface, you get into some tangent line kind of things, tangents to a curve. That was one of the things. And then the whole thing about rates and how that evolved, slopes and rates and all the things it added. And so all those different uses for that is what made derivatives such a kind of an important deal. And then the fact that this idea of area, which was, again, back in those days, a lot of value was placed on land ownership. The rich people were the people who owned land, and the people who didn't have a lot of money were the ones who worked for those people who owned the land. And so a lot of the money was through bartering and trade and so forth, and goods and services and kinds of things, as opposed to monetary things. So knowing how much land you had in the areas of those things, that was an important thing. And so when you had odd shaped and misshapen pieces, and finding that area to a relatively, accurate degree, and then of course that led to the thinking about that, how we configure that, and so forth. So you have the geometric shapes, but then what about these odd shapes? And then the idea of fitting curves, fitting equations to curved surfaces, and so forth. So you can see where this would go. So we now, if we can fit a mathematical equation, mathematical model, to curves even on the top or the bottom or the sides of a region, then we can find that area, okay, using this process. So that's what we're doing, so area between curves. Now, the key thing that we came up with is, what we do is essentially we divide the region into some strips, and rectangular strips that we can then find the areas of. And then the integral adds up those strips. So we can either do it with vertical strips, or we can do it with horizontal strips. And so if you're setting up with vertical strips, is what we're used to, then the width of the thing is a delta x. The delta x turns into the dx, and so your integral is going to be in terms of x's. All right? And so you always want your equations in those cases to be y equals, because y equals in terms of x. And that way your integral is in terms of x, all right? But the new part that we kind of discovered yesterday is we could also divide the region into horizontal strips. Well, if you add up horizontal strips, their width is delta y, which means the integral will be a dy, which means it's in terms of y, which means you want to describe your equations as x equals, kind of the inverse situation. So you want to solve for x and get them in terms of y. So we got to keep those two things straight, all right? That's first and foremost. Okay, so let's talk about number 3. So in problem number 3, they had this region. Let me, let's move this over a little bit. And it was a region that you were given back in figure 4, I believe, back in the book. So it was given back on a previous page. I think it's on page 415. But now, what I want you to read carefully is in problem 415, they worked it one way, but in exercise 3, they decided they wanted to do the integration in x. That's what the directions say. Integration in x is used to find the area. So that means what kind of strips? Integration in x. Okay? In x means that with the integration is with respect to x. If it's with respect to x, that's what we're used to doing, and what we're used to doing is vertical strips. So they want you to do vertical strips for this problem. So what they have done is they went ahead in parts A, B, and C is they divided the region up for you. But let's go ahead and do it. Go ahead and do the region. So the region was, one of the equations was x equals, what was it? 4 minus 1 minus y squared. What was it? 1 minus y squared. Okay? And the other region was y equals 1, y equals negative 1. No, the original region. The original region back in figure 4. It was y equals 1, y equals negative 1. It was x equals 1 minus y squared, and it was x equals y plus 2. It was these were the 4 regions back in on page 415. Okay? So that's the original region. So let's go ahead and graph this. Okay, so you guys already had a picture of it, but what I want to make sure we can do here today is we can, given an equation, get your calculators out, okay? Given some equations, you could graph. I didn't see a lot of graphs on the papers. I just saw some. I don't know if it specifically said to graph on some of them, but on the ones I do, on the quiz that we do over this, I am going to say in almost every problem, sketch the region. Almost every problem we do in the rest of chapter 7 is going to involve some region. And we're going to do something with that region, those graphs. So we've got to be able to graph, you've got to be able to draw these regions and understand what region they're talking about. The difficulty is these ones where they got it solved for x. Okay? So one option you have to graph them, especially if you're going to use your calculators to do what? Get y by itself, right? So one option you have is to get y by itself. So for this one, we can do y equals, let me do those in red. Well, no, that's okay. So one thing here, so we can get y by itself, so y would equal x minus 2. So that's one thing we do. That might make it easier to graph, because to be honest, sometimes these are simpler to graph by hand than to go to your calculator by the time you set your window and do all these various things. But if you want to put it in your calculator, you got to do this. Now, if I solve this one for y, what would happen? Well, let's see. If I add the y squared over to the other side, I'd have y squared. If I subtract the x, I get 1 minus x. Then I square root both sides. You cannot forget to do plus or minus when you do the square root. Okay? It would be nice if you could notice that this is a parabola. Now, we discovered something in the other class. I knew about it, but I'd forgotten. Somebody asked me if we could graph these on our calculator, and I said no. In other words, with x equals. If it's f of y, well, f of y just means x equals. But we actually can. Did anybody notice that? If you go, everybody, let's do this. Now, I'm not saying you want to do it. I'm not saying I'm going to give you very many of these type of equations where it's x equals, but I may. Okay, you always have the option to solve for y. Now, there are times where you can't solve for y. I don't think I'm ever going to give you one that's an x equals and you can't solve for y. I don't envision that. Okay? But if you go to your calculator on the graph screen, go to the menu, go to graph entry, and go down, I think it's number 2, equation. You see the equation option? And then you've got parabola, ellipse, and all those. The reason I forgot about this is they just added it with the new software update. Is there anybody that doesn't have it? I think we updated everybody. Okay? Go to the parabola option, and you see the 4 choices? You see how the first 2 are upwards parabolas and the last 2 are sideways parabolas? Now they got vertex form and standard form. Now which one is ours in? Ours is in standard form. Very rarely will we have them in vertex form. Actually, this is a simple enough one we can probably do both. But I would go down to standard form. Okay, so choose standard form. Do you see how you now fill in the boxes? Okay, so you can now fill in a what for the first box? Would it be -1 in front of the y squared? And the second box is in front of the y, so that'd be 0. And the last box would be a 1. And then hit enter. And it'll graph that sideways parabola for you. So that's kind of nice. Okay? But you could stay in regular function mode too and get it y by itself. All right? Now, the line is pretty easy to solve for y. So anyway, what is this? This is a parabola that, goes through 1. Let me go back. So that goes 1, 2, 3, 4, 5, and so forth. All right, and 1, 2, 3. Okay, so this is 1 to the right, and then it opens to the left, right? Is that correct? So it crosses, so here's -1, here's -2, and so forth. So it's a parabola that kind of comes up like so, does that, and comes down like so, and does that, right? So that's the parabola that we get. Now here's another thing you could learn. I know you haven't done much of this, but whenever you have this, back in Algebra 2, you did this work with parabolas, probably in Advanced Math too. But this is just a parabola that's a sideways one, and so if you look at it, it's simply x equals negative y squared plus 1. Well, it's the same sort of shifting that we do with our regular functions. It's just sideways. So instead of this plus 1 being a shift up, what is it? It's a shift to the right. And then this negative, instead of making it go from up to down, it makes it go from opening right to opening left. And so, again, it wouldn't have been that big of a deal, I don't think, to just be able to graph it by hand if you just know a couple of those little things. All right. Anyway, we could have graphed it in our calculator like this to get it that way as well. All right, then we graph this line, y equals x minus 2. So it goes through here, up 1 over 1, up 1 over 1, up 1 over 1. And so we end up with this line like so. All right, and then we've got y equals 1 is a boundary, so that's this line up here. And then we've got y equals negative 1 is a boundary, so that's this line down here. So we're looking for this black region right through here. That's the area we want. Now, the easiest way to do that would be what? No, I'm not talking about problem 3 now. I'm just saying if I would have given you these graphs and said find the area of that region, would you have wanted to do horizontal strips or would you wanted vertical strips? Horizontal would be the best because a horizontal strip is going to touch the line on the right and it's going to touch the parabola on the left. And you might think, well, it's the top and the bottom half. No, if we use the x equals equation, it's just the whole parabola is that equation. So the right x would have been the line. So let me write that in black down here. So we would have done right minus left. So I know you didn't have to do this in number 3, but right x coordinate is the line, and so it's x equals y plus 2. So the right x coordinate is y plus 2 minus the left x coordinate. The left x coordinate is the x coordinate of the parabola. The x coordinate of the parabola is 1 minus y squared, right? Because it says x equals 1 minus y squared. So that's the x coordinate of the parabola. So 1 minus y squared. And those strips would fill the space from where to where? Negative 1 to 1. The strips would fill the space from negative 1 to 1. Okay, so the integral would go from negative 1 to 1. And that would be it. There's our dy. And we can type that in, and what is it, like 125 over 6? Is that the answer to that one? It's like 125 over 6. Oh, okay, I knew that sounded familiar from sometime. What was this one? What 3 come out to be? Your final answer, part D. Yeah, that's what it was, 2 and 2/3, that's right. 8/3, 2 and 2/3, okay? That's what it should come out to be if you type that in. Okay, now let's talk about problem 3. So problem 3 broke it down. So Spencer, you said split it apart, right? If you want to do vertical strips, let's do that in red here. If I want to do vertical strips, I got a problem because right here the vertical strip is going to touch the top. The top y value will be that line. The bottom will be the parabola. But if I do a vertical strip over here, it touches a line on top, but it touches that line on the bottom. And if I do a vertical strip down here, it touches the parabola on top and that line there on the bottom. So I got 3 different areas. Okay, and so we have to split this apart, and that's what they do. So in part A, and you've got to be able to read these regions. Okay, so let's go through it very carefully. So in A, it says, find the area of the region bounded below by the x-axis. So there's the x-axis right there. Above by the line y equals 1. So that's up here. On the right by the line x equals 1. That would be right here. X equals 1 would be this line right here. That's the right boundary. And the left boundary is the parabola. That's right here. So they're talking about this little piece of area right in here. Okay, so this little piece is what they're finding in part A. So it would be this strip. So let's write that integral. So it's top y value. What's the top y value? 1 minus the bottom y value. What's this y value right here? Right? Because it's y equals. It's got to be y. That's why I always say to myself, when I'm doing top minus bottom, I always say to myself, top y value minus bottom y value. Okay, the y value here is 1 because it's y equals 1. And the y value here is y equals the positive square root of 1 minus x. It's positive is the top half, negative is the bottom half. We're doing the top half here. So square root of 1 minus x. And then dx. And then these strips go from where to where? 0 to 1. So you do that, it comes out to be 2/3. No, 1/3. 1/3. Okay? So now do this one down here. It's the same. Now you do part B, it's the same thing. Well, it ends up being pretty much the same integral. Because now you're going to do the top y value, which is the bottom half of the parabola, so that's negative radical 1 minus x, minus the bottom y value, which is negative 1, and those end up turning into plus, and lo and behold, if you look closely at that, that is exactly the same integral, right? Except it's from, well, no, it is exactly, because it's from 0 to 1. The strips fill the space from 0 to 1, so it ends up being exactly the same integral, so it's 1/3. So that's part B. Part C says then to find this other region, bounded on top by this line, on the right by this, on the left by x equals 1, so that's this region here, so it would be this strip right in here. So the top y value is 1, the bottom y value is that line right there, right? The y equals, okay? You want the y equals 1, so that'd be x minus 2. And then those strips fill the space from 1 to 3. And then that comes out to be 2. And so you add that all up, 2 and 2/3, and that's part B. So that's a pretty good problem in one where you might have to split it up versus it'd be a lot easier if you did horizontal strips. And what's it look like? It really lets you get into this whole thing in the top and bottom half of the graph, you know, where it can get kind of complicated. Some of them are much easier than that, but that's something that could happen. Okay, let's skip number 10 for a minute and come back to that one. Let's go ahead and what was the other one you said? 23. Okay. Just to make sure we're clear here. So on 23, they give you x equals y squared minus 4. So you can graph this with our newfound equation graphing feature on our calculators. And then y equals 2 minus x. So this isn't a whole lot different than the last one. So when I go to graph those, again, I would look at this. I've done enough of those to remember that, okay, this is a sideways parabola. What would that minus 4 mean? 4 to the left, right? And then it's just a normal parabola opening to the right. So I would probably plot a few points just to see what I would do. Like x equals 0 would be a good one. So if I get 0 there, I get plus or minus 2. So that's going to cross there, cross there. So it's going to come in here something like so. Come down like this, like that. Down here's 1, 2, 3, 4, 5. All right, so I think this ends up crossing right down here somewhere. So we have y equals 2 minus x, so that'd be the same as y equals negative x plus 2. So that's a y-intercept of 2, down 1 over 1, down 1 over 1. Over 1. So there it is right there. So it crosses down here at what, 5, negative 3? And it crosses up here at 0, 2. So this is the region we're talking about. So in problem 23, you were supposed to do what? What kind of strips? Vertical. So do we have to split it up? Yes. Because over here, your strips are going to touch the top and bottom half of the parabola. And over here, your strips are going to touch the line on top and the parabola on the bottom. So we have to split it right here at the x or at the y-axis right there. We've got to split it. Okay, so if you're going to do vertical strips, you need to have y equals. So we've got to solve this. So this would be plus or minus square root of x plus 4. Add the 4 over there, square root, top and bottom half right there. So this first strip, so this region, this first blue region right here would go from where to where? Negative 4 to 0. The top y value is positive square root x plus 4. The bottom y value, okay, and then our dx, that turns to plus, so you can just add those together and have two of them. When you type it in, save your little typing, whatever. Then we're going to add to that this other region. That integral is going to go from where to where? 0 to 5. The strips fill the space from 0 all the way out here to 5. And it's going to be the top y value, which is the line, 2 minus x, minus the bottom y value, which is the bottom of the parabola, which is minus a negative turns to plus. Right? Top minus bottom. Add those all together. There's our 125 over 6. Right? Now, it's important that you do one like that because we may get into some equations I showed you yesterday. You may get an equation like y equals x cubed plus x squared minus 7. You cannot solve that for x. You cannot get x by itself. You cannot do horizontal strips if that's the case. If you can't get x by itself, you can't do horizontal strips. So you might be forced to split it into pieces. Okay? You got to know that. All right, now when we go to number 35, they wanted us to do horizontal strips. A nice thing about horizontal strips, wouldn't that be what you would have chosen here if you had a choice? I think if you're smart, you would have. Because horizontal strips are going to be, you're not going to have to split it. Every horizontal strip you draw, and that's the test. Every horizontal strip touches the same curve, the line on the right, and it touches the parabola on the left. Now, there is no top and bottom half on the parabola when you're doing horizontal strips. Because when you're doing horizontal strips, you got to solve for x, and this is the parabola equation. This one equation. There's no plus or minus. Okay, when you're doing horizontal strips, the whole parabola is just the one equation. All right, so we got our integral. The length of the strip is the right x, which is what? We don't have that yet, do we? Yeah, we got to solve this for x. So we add the x over to that side, we subtract the y, we get 2 minus y. Okay, so the right x is 2 minus y. The left x is the x on the parabola. That would be y squared minus 4. And then those strips fill this space from -3 up to 2, right? The y values from -3 up to 2, the strips fill the space. You type that in, and you should get 125 over 6. All right. Now, something, and I think it's going to be in your homework today, something that's important to understand here, and we're going to get into this as we talk about 10 and just a variety of problems. And then the new thing we're going to learn today. We are now getting into a situation where an integral for us is starting to take on different meanings. In the beginning, and it's already kind of doing that, but we haven't talked about it really. If I just write this integral, right? The answer to that is some number, right? I mean, maybe it's 7, I don't know. It's just some number, right? It's a definite integral, just some number. What does it mean? What's it mean? What's the first thing that comes to mind when I say, what's this integral mean? Area. Height times width, right? Area, it should be. I would agree. That's the first thing that should come to mind. It's what area? That graph, which would be a parabola shifted down 7, so clearly it's not probably 7. Shifted down 7, goes up like so. Area from 2 to 3, I don't even know where 2 and 3 are here. Maybe they're out here, whatever, maybe it is, I don't know. But you would be thinking about a piece of area, right? That would be 7. All right, and you would be right. That's what that would mean. That would mean the area under this function. Okay, but what if I told you that this was an equation that stood for the velocity of a car going eastward in feet per second. Now what would that 7 mean? Let's be specific. It would be feet, net distance traveled, eastward. If it's negative, it would be west, and you're still leaving something out, between 2 and 3 seconds. So in the interval from 2 to 3 seconds, this car, whatever, had a net distance traveled 7 feet east, right? This car, whatever, person, probably not a car, feet, but this, whatever, in that second, from 2 to 3 seconds, it gained in the eastward direction 7 feet of distance. It's 7 feet farther than it was at 2 seconds. Does that make sense? And that's a little bit of what number 10 was about. Okay, so this integral has a whole new meaning now. Area doesn't have any role there in that description. Okay, now, really throw a curve at you here. This could mean a different... This could mean a different kind of area. Couldn't this be a top minus bottom? And it's got a minus in it, right? What other area could this be right here? What would be the two curves? X squared, y equals x squared, and y equals 7. From to, I don't know where 2 and 3 are, but, right? It could be that piece of area, right? Kind of tilted, but if this was 2 and this was 3, it would be, oh, I got that backwards. I didn't do top minus bottom. I did 7 minus x squared. Okay, so let's assume, because, well, that's why I said I didn't know if this is negative or not, right? Remember when we do area between curves, it's always positive. So let's assume, let me redraw that. So let's assume here's our parabola, here's y equals 7, and here's 2 and 3 out here. Okay? So here's 2 and 3, so out here and out here, so we would have this region right here, and it would be that region right there. So from x squared down to 7. So top y value x squared, bottom y value 7, x squared minus 7 from 2 to 3. It's that piece of area, which is a totally different piece of area that we were talking about on this over here. Okay, we graphed x squared minus 7 as our function and did the area between it and the x-axis. Does that make sense? So these integrals, all of a sudden, we get the understanding that when you do a definite integral, it's just a number. What it stands for depends in the context of the problem. And we're going to learn a new one today. Okay? But it could represent a lot of different things. And then the other thing to keep in mind is when we have a definite integral, we have a lot of different ways to find it. If I just give you this definite integral and say, okay, now solve it. What do you think about the last couple of days? What are you going to probably do? Any way you want. And you're going to grab the calculator and you're going to type it in. Right now, 90% of the time, that's what we get to do. If we have a definite integral, it's just a number, and what we want to do is find that number. Well, most of the time, if you're not told otherwise, type in your calculator and do it. But what if you couldn't? What if I said you can't do that? That's fundamental theorem part 2. Nice one because you can do the antiderivative. What if it's one you can't do the antiderivative on? If we can't do the calculators, and we can't do fundamental theorem part 2, and it's probably not geometry, so it's an approximation. So like on today in the homework, they said do 5 midpoints. Right? People get all confused when we run into problems and say use 5 midpoint rectangles to find the area between the curves. Well, they really get confused when it says use 5 midpoint rectangles to find how far the car travels. Well, you're not using 5 midpoint rectangles to find out how far the car travels. You're setting up an integral to find out how far the car travels. You're using 5 midpoint rectangles to then do the integral, to approximate the integral. Does that make sense? So before you ever do 5 midpoint rectangles, fundamental theorem part 2, or whatever, you first set up the integral that will make it happen. Then you go from there. Now, what if they want you to do 20 midpoint rectangles? The RAM, somebody there said RAM. I said, what do you do if it's 20 midpoint rectangles? I said, RAM. That case. Then ram it. Oh, that's good. Yeah, that's what we'll do that now. So if it's more than 10, remember, to do 20 midpoint rectangles? Ram it. Okay. But you go to that area document, because I think you have one of those on homework today. Okay? But you set up your integral first. Once 20 midpoint rectangles, go to your calculator and use that area document and do 20 midpoint rectangles. Okay, because those are still viable options. We're just not going to spend much time on those anymore because we spent our time on those. But when we review for a final and those kind of things, you know, they're going to come up. And so we want to still be able to do those. But most of the time, we'll just type into a calculator. All right, now let's talk about number 10. Number 10 said, you had this integral from 1 to 3, f of x dx, or f of t maybe it was, f of t, okay. But that was, so the x or the t, that was time, right? And it was, well, I think it was seconds, most of them, well, no, I guess it changed. So then they told you these different things. So some of them are pretty easy, but some of them get a little tricky. So the first one they said, okay, f is going to be upward velocity. Okay? So what will this integral represent if f is upward velocity? Net distance traveled between 1 and 3. Now what if, and then it says, consider what happens if your answer to this is negative. Then its net distance traveled was negative. It went down. So it was farther down after 3 seconds than it was when it started at 1. That's important to understand. There's some intricacies here that we got to get. That it's net distance, okay? It's the accumulated change. It's the amount of change. So if this is a rate of change, in other words, feet per second, I think that's what it was, right? Feet per second. Then the integral is the amount of feet that it changed. How much feet changed, how much the distance changed. Okay? So if it's negative, it changed in the negative direction. Okay. That's not too hard to understand. And I'm going to skip B for a minute, go to C. So if F is how much water, the rate it's flowing in the tank, which is liters per minute, then what's this integral? Net change in water in the tank, right? And if the answer is negative, you lost water. Water's coming out of the tank, right? So there's less water in the tank. So it's the net change in liters. Again, that's a pretty easy one to grasp. All right, and then let's do D. If F is the slope of the G graph, then what is this integral? Okay, that's a little trickier. Let's think about what slope is. It's the rate of change of the steepness of the, it's just the amount of change that the G graph had. It's the change in the rise. Think of it this way. Think of it this way. We just did feet per second, and when we did the integral, it was feet, the top unit. When we did liters per minute, and we did the integral, it was liters. When we do the integral of slope, it's rise over run. So what is the integral? The rise. It's the net change in the rise of the graph. So if you're doing the integral of an f prime, a slope, right, then the antiderivative is the amount of change of the rise. Because really what slope is the rate of change of the rise. Right? That's what it is. Rise over run. The change of the rise. Okay? So the integral is the total amount of change in the rise. How far did the graph go up? And if it's negative, the graph what? Went down. Okay? So that's that. Now, here's where it gets tricky, is this acceleration. We spent way too much time this morning talking about this, so I'm going to try to shorten that a little bit today. But if you do the integral of acceleration from 1 to 3, which is feet per second squared, somebody want to take a crack at this one? It's the net change in velocity. Now that's a pretty, that's correct, but do we really understand it? So if it's negative, what's that mean? The word slow down or speed up should not be a part of this. the velocity decreased. There was a total change in velocity. The velocity decreased. But here's why we can't say speed up or slow down. I think this is worth spending a little bit of time. Just because velocity decreases, and let's look at a couple of examples here. Because I agree with you. If the velocity is negative, if the integral of this is negative, then that's not going to mean speed up or slow down, because let's see, what would be the quick easiest way? Let's do an A graph right here. Okay, so let's say you had an A graph like this. Okay, right here the acceleration is positive. Let's think of the chart. This probably helps us the most. So if the acceleration is positive, what's that tell you about the velocity? Increasing. If the acceleration is decreasing, which it is right through here, what's that tell you about velocity? Now does concave down. Does concave down tell you anything about velocity, whether it's increasing or decreasing? It does not, because let's just think of a velocity graph. If I have a velocity graph that was up here, what's happening? Is this thing speeding up through here? If this is the velocity graph, speeding up, right? And then slowing down. But what if it was this? Now what's happening? What's happening right here? Slowing down. Why? Because these are negative but getting less negative. They're heading towards a zero velocity, right? Zero's right here. So it's heading towards a zero velocity, so it's slowing down. Now it's, see how that's opposite? And here's the thing. If all we know is think back to what we learned in chapter 1, or early chapter 2. If you know the f prime graph and want to draw the f graph, what's the problem? If you have the f prime graph but want to draw the f graph, you don't know the shift, right? Well, isn't that what we're talking about here? If all we know is the acceleration graph, and we want to look at the velocity graph, couldn't it be either one of these two situations? Because we don't know where the shift is. So if all we know is acceleration, we do not know if it's slowing down or speeding up, right? If you throw a ball in the air, what's its acceleration? Negative 9.8 meters per second squared all the time, the whole time. When you throw a ball in the air, its acceleration is negative the whole time. It's being pulled down. You throw a ball in, is it speeding up or slowing down? Well, it depends. It's slowing down for a while, and then it's going to be speeding up. So if all you know is its acceleration is negative 9.8 meters per second squared, you do not know if it's slowing down or speeding up. Okay, it depends if it's going up or going down. So that's important. All right. So anyway, in the answer to the question, what I'm saying to you is we want to talk about it's the net change in velocity, but that does not mean anything about speeding up or slowing down. It just means the change in velocity was negative if the integral is negative. Okay, so you just got to be careful what we say there. That's a harder one to grasp. It's easy to grasp a change in miles because that's your distance you travel. The change in liters because that's the amount of water. The amount of rise of the graph, that's easy. But a change in, or an amount of velocity is harder to grasp onto. And so that's just something, you want to be careful with the term speeding up, slowing down. Okay, what I would like to do, and this is going to mess up for the people who we're recording today, again, I apologize. So, well, in a little bit it will anyway. Here's what we're going to do. If you want to jot down some notes about this real quick, and then we're going to come up with a formula. Here's what we're about to embark on. We are going to, it is quite a journey, yes. It is one of my, well, I said this second block, it's one of my favorite things. Pretty soon when I say that for like 100 different things, you probably,
I think you just really like math.
I don't know. This is really kind of a neat thing. Now, here's what it is. Length of a curve, or it's sometimes called arc length. Now, the arc length you're used to is on like a circle, like unit circle. You talked about arc length, okay? And that's fine because we have a formula for the length of the distance around a circle. It's 2 pi r, the circumference. So if you want to know the arc, if it's a perfect circle, if you want to know that length, we have a formula for that, okay? And then if it's part of a circle, you just take the fractional part of 360 degrees and whatever. Okay, but I'm talking about length on a parabola or a sine curve or something like that. How do we measure that distance? If you have, I mean, think about that. If I wanted to know how far it is from here to here, if I gave you a piece of paper with this big curve on it and said, how long is it? What would you do? How would you straighten? Well, okay. Put a piece of string on it, right? Get a piece of string or yarn or something, lay it down on it very carefully, and then straighten it out and measure it. Because the only really way to measure length is straight, linear length, right? And it's like when we do distance between 2 points. We do horizontal and vertical, right? Linear kind of lengths. We can do that. But we can't do length on a curve, and like I said, unless it's a circle, because we have a special formula for that. So you can already see kind of a connection. When we want to do strange areas, we can do geometric shapes, the kind we have formulas for, or, you know, we couldn't do them. So what did we do? We did rectangles, something we could do, and then and this is the part I really like about this, we figured something we could do, like rectangles, and then we applied that and did infinite rectangles. Don't know how to do slope at 1 point? We did 2 points, and let it get really close until it became 1 point. So the same idea is going to happen here. So the only thing we really know how to find is what? Straight lengths. So how about we try to make this straight? Okay? So, now we can't really pull that curve and change that curve, so how about we divide it up? Right? How about we take that curve and we divide it and we find that length? Now here's what we're trying to find. We're trying to find this length right here. Trying to find the length of this parabola from here to here. Well, that's not a very good approximation, right? So how about if we do that? Well, I'm not sure about triangles. It's lengths we're talking about. Can I find that length? Sure, Pythagorean theorem, right? I can just do Pythagorean. Because remember, I know what this curve is. So I can find this point, I can find this point, I can find this point, because I know the equation for the curve. So I can find those points. And now I can just do Pythagorean, which is a distance formula, right? Pythagorean theorem is just a distance formula, right? This minus this, square it. This minus this, square it, square root of all that. I got the hypotenuse, right? That's Pythagorean theorem. So I can find that length. What would be better? How about if we divide it up into 3? Or 4 lengths? Or 5? Right? And you can see what's happening. Right down here we got an approximation of all these red lengths added up together. And eventually, as we keep going towards infinity, right? Now it says 11.27, 11.28, 11.29, right? 11.3, and eventually we're going to start, now it's 3.0, you know, at some point we're going to get, so we got 50 little links there, and we're getting more and more accurate, right? Same idea. It's the same concept of every important thing we've learned about. Area, slope, you know, those kind of things, is we get better and better approximations. So here's our job on this. And maybe I'll go through the PowerPoint without doing the slideshow. Well, that's not going to work. Well, we can make it work. So here I've got the PowerPoint here, and we'll just take it line by line right now. So what we've got is, let me explain this. You do not have to write all this down. We're going to end up with this formula in yellow, which I'm going to rewrite a little different here when we're done. But so what we're doing is we're going to say, okay, let's take this little piece right here. Now they call it DS. I wouldn't really pay too much attention to the left side of this. I don't think that's a big deal. Okay, that's not how I would normally work this out. Okay, but so we want to find this length right here. I want to find that length to that one piece. Now what we did, if you remember what we did with area, we said, okay, let's take the height of one rectangle times the width of one rectangle, and then let's do a sigma notation, right? And let's let the sigma add those up. Now the sigma ended up turning into what? Ended up turning into an integral. And then the delta x ended up being the dx. And what we find out here now is if we want to use the integral as an adding machine, which is great, we just talked about that, that's what we wanted to do. The key is when we find that or set up that integral, we need this dx piece. We need there to be a dx in there. And the dx has to represent that thing that goes to nothing. Now for area, it was always width. We had height and width, so it was a very easy one to do. Height ended up being function, and delta x ended up being the the dx piece, the piece that disappears, that goes to nothing. Okay, so we're going to do that here. Now, as these get littler and littler, which piece is disappearing? Dx. Well, the dy actually is getting smaller and smaller too, but less so, especially if it's steep, right? But as we get smaller and smaller and smaller, again, the dx, I would probably call that delta x, right? To fit in with what we did before, but it's going to be getting smaller and smaller and smaller. It's going to go away and end up being the dx part of our integral. Okay, so here's what this looks like here. So this length we're looking for is just this squared plus this squared and then the square root of that. Okay, so that's what we got right here. Now the problem is I want to put the integral on that to add it up, right? The integral, I'm skipping a bunch of steps in here like with the sigma and stuff, right? We don't need to go through all that again. So the sigma is adding up all the pieces. Instead of adding up these areas, we're adding up these lengths, right? Make sense? So the problem is we need to get the dx out of the integral here somehow. How can we do that? Well, they do some fancy algebra in this step right here. Look what they did. They said, okay, let's just multiply this inside. Let's multiply the inside of the square root times a fancy 1. Dx squared over dx squared. You see that? They took the inside and said, let's multiply it by 1. That doesn't change a thing, right? Multiply by 1. Now, what does that mean? Well, whenever you multiply two fractions, you just multiply straight across, right? So what they did is they multiplied across the bottom and moved that dx squared to the bottom here. Then they went ahead and split it apart, right? You can always do that in a fraction, split it apart. And then that leaves you this dx squared here. Okay, so look what we got. We got the parentheses times that. Now, you know in an interview, hopefully you remember in a square root, if I have square root of 40, I can break that into square root of 4 times square root of 10, right? I can split that into two pieces. Well, that's what we're going to do here. We're going to split this part, and then we're going to split out this part. Now, that'll be square root of dx squared. Well, what's square root of dx squared? Dx. And that's how we get our dx out of there, because we need it to be out of there, because we need that in any integrals that we have. We need that dx piece. Okay, what's left in here? Well, we got this dy squared over dx squared. Now, anytime you, another algebra thing here, anytime you have a top and bottom squared, you can make it this, make the whole thing squared. So dy squared over dx squared is just this. Now, what's dy over dx? It's just a derivative. Oh, that's cool. That showed up out of nowhere. The derivative, dy over dx. Now, remember what's happening. Dx is getting really, really small. So what's happening? This point and this point are becoming 1. Oh, yeah. It's a derivative. Okay, so that's y prime. Or they went ahead and used dy dx. I'm going to use y prime. Or usually we have a function notation, so that would be like your f prime. And so there it is. There's our formula. So all I really need you to know about this is this formula. And use the formula. And then you get to use your calculator to find it. But I think it's important to understand where it came from. Okay, important to understand it just simply came from Pythagorean theorem and finding these littler and littler pieces and adding them up. All right, so what you need from this is that you can put in your notes is this formula right here. So the length of a curve is the integral from a to b of 1 plus, I'm going to write it as f prime. You could write it as y prime too if you want, depending on the problem. A lot of times the problems are given as, whoops, that's a dx, not a dy. That is the length of the curve f of x from x equals a to x equals b. Okay? So if f of x is the curve, then this integral will give you the length of that curve. But again, we talked about earlier, remember when we said an integral is just a number? This integral, we'll work one here in a minute. When you type that into your calculator and it spits out a number, does it know it was doing length of a curve? If the calculator could think, it might think you were doing what? Area. It might have thought you were doing the area under this function, right? Or it might have thought you were doing miles or your feet or whatever, right? I mean, it means a lot of different things. But here we got a case where this integral means length of the F curve from A to B. All right, so there's an example here in on the PowerPoint. Let's go look at it here. Okay, so it would be given like this. So if y equals negative x squared plus 9, you want to do the length of the curve from 0 to 3. So here's the graph of, that's just an upside down parabola shifted up 9, so we want the length of that curve. Okay, well, we need the derivative, right, because the formula needs an f prime in it. So we do the derivative, negative 2x. So we go over here and we put it into our formula. 0 to 3, negative 2x is a derivative squared. Just like that, we just type that into our calculator. We get 9.747. That is that length. And that makes sense because it's definitely bigger than 9. I think in the PowerPoint here, they actually, at one point here, yeah, let me go to here, they actually said, well, let's just calculate that, do the Pythagorean theorem. So 9 squared plus 3 squared would be the square root of 90, 9.49. And it looks like it's a little longer than 9.49, sure enough. Okay, so the length of the curve. So we just need to know that formula. Okay? All right. So your homework, now, is there anybody going to be on tomorrow? Who said they were going tomorrow? Okay, let's dig out your packets. I've got a couple of things I want you to pull out here. Some of it related to today's homework, some of it related to tomorrow's homework. So, in the first thing I want you to find is this LH packet.
No, I made that noise because I didn't think I could find it.
That's what I know. That's what better not.
Is it this one?
It's the one that's a little skinny with a few pages, got Sigma on the front page. 279 is the front page.
Dang.
It's got a bunch of Sigma props. Yeah. How long ago? Chapter 5.
10,000 years ago.
270, that right there. 279. Okay, so you need that, so set that aside. All right, then we had another packet that was, I call the motion packet.
Oh.
Now it says, yeah, let me see it. It says worksheet 1 on the front page, what you need to know about motion on the x-axis. Worksheet 1, what you need to know about motion.
What chapter was this in?
I have no idea. Somewhere around chapter 4. Good organization.
Because all of my chapters are.
And we've done part of that packet already. Okay? Neil. All right. Now you guys are gonna be gone tomorrow. You'll be back Friday. Randy, you'll be back Friday. You'll be back Friday.
Is mathematics necessary?
All right.
No. Is this the right one?
That's right.
Yeah, let me see it.
Okay.
Hey, I found it. Oh, God. I remember not doing that though. I remember not doing it too.
All right. So now get out your assignment sheet. Okay, your assignment sheet, and your assignment sheet is, or your assignment. All right. So on your assignment for tomorrow. Okay, your assignment for tomorrow is these two right here. Okay? Now, 7.1, that's in the book. Okay, and 7.1 is mostly this new thing that we just learned. Mostly, I think it's got some questions about, I think it's got one question kind of about those units again. You know, the units and what the integral means. But that's mostly this new thing we learned, which is length of the curve. And then this is in that LH packet. It's the last page in that LH packet, page 409, 410. And that is more of the area, the thing we did yesterday and what today's homework was about. So it's more practice with that. So that's area between curves. Okay, so we're going to practice a little bit of both of those. So do those two for tomorrow. Now, those of you that will be gone tomorrow, that motion packet I had you get out, we're going to finish that. I think we've already done up to number 15. We're going to finish that. Okay? And work on that. I think that might be all we do tomorrow. Okay, and then, so there may not be a video unless it's a video of me going over the homework, you know. So if you had questions on the homework, you might look out for that. But otherwise, if this homework's okay, probably don't need to watch a video. All right, and then Friday, I'm not sure yet. On Friday, it may be some more packets review time, and then next week we have our famous Lemon Lab. So, Lemon Lab.
How can it be famous
If you've never heard of it, okay. Infamous.
Infamous is famous for God.
In my mind only. We'll be slicing up some lemons, finding the volume of lemons. That's next week. Monday or Tuesday, I'm not sure.
What?
Ah.
Your laugh wasn't horrible. Sometimes